Somewhere in the western Pacific, roughly 230 kilometers north of the last inhabited edge of the northern Mariana Islands, there's a mountain that almost nobody has ever seen. It does not appear on any skyline. No ship's captain has ever watched the sun set behind its peak. And yet, on official United States government maps, it carries a name, a number, and something that very few mountains on Earth are ever given: a live threat classification updated week after week by scientists who have never laid eyes on its summit. That mountain rises nearly 2 kilometers from the floor of the Pacific Ocean, and it stops, almost mockingly, just 55 meters short of breaking the surface. 55 meters. Close enough that a large eruption could, in theory, blast debris into open air. Close enough that a passing fishing boat could sail directly over the crater, without a single instrument on board ever knowing it was there. And in the last week of July 2026, the United States Geological Survey did something it does for only a small number of volcanoes on the planet. It issued a formal alert. Not for mountain that smokes, not for mountain that rumbles the ground under a nearby town, for mountain that nobody can watch, sitting under a stretch of open ocean so remote that the nearest permanent seismic station is hundreds of kilometers away. The alert level was set at advisory. The aviation color code was set at yellow, and buried inside the dry, procedural language of that bulletin was a sentence that should unsettle anyone who has ever set foot on a boat in the open Pacific. The lack of local, real-time data means we are unable to forecast or warn of impending eruptions. In other words, the United States government is watching a volcano it cannot actually watch. It is sounding an alarm it cannot fully hear. And somewhere beneath 55 meters of blue water, something that has erupted at least 11 times in the last 10,000 years is sitting quietly within reach of the surface. The volcano's name is Ahi Seamount, and to understand why a government agency would issue a public notice about a mountain nobody can see, you first have to understand where it sits and why that location matters. Ahi lies at the northern tip of the Mariana Arc, a chain of underwater and island volcanoes that curls south from Japan through Guam and down toward Papua New Guinea, tracing the exact line where the Pacific tectonic plate is being forced downward, inch by inch, beneath the smaller Philippine sea plate. This is subduction in its rawest form. The Pacific plate does not go quietly. As it dives into the mantle, it drags water and sediment down with it, and that water lowers the melting point of the rock above, generating vast reservoirs of magma that rise back toward the surface wherever the crust is thin enough to let them through. Ahi is one of those release valves. It sits about 18 kilometers southeast of Farallon de Pajaros, also known as Uracas, the northernmost island in the entire Mariana chain, and one of the loneliest scraps of land in the Pacific, uninhabited, wind-scoured, and rarely visited by anyone other than the occasional research vessel. From that empty island, Ahi's summit is closer than most people's daily commute. And yet it has taken scientists decades of scattered, accidental encounters to even confirm that it is there. The first hint that something was alive beneath the water near Uracas came in 1979, and it did not come from a scientist. It came from a fishing boat. The crew working the waters near the seamount felt something the human body is not built to register at sea. Shocks, actual physical shocks, rippling up through the hull from beneath them. Moments later, the water around the boat began to change color and smell of sulfur, the unmistakable signature of gases and heated mineral-rich fluid pushing up from somewhere below. There was no eruption column, no ash cloud, nothing a satellite thousands of kilometers away could have detected. Just a boat, a crew, and the sudden visceral knowledge that the seafloor beneath them was not as solid or as silent as it was supposed to be. For more than 20 years after that, Ahi went quiet, at least as far as anyone on the surface could tell. Then, on the 24th of April 2001, something happened that no human being witnessed directly, but that the Earth itself recorded. An explosive submarine eruption sent seismic waves rippling outward through the crust and the ocean, and those waves were strong enough to be picked up by a seismic station on Rangiroa Atoll in the Tuamotu archipelago, more than 4,000 kilometers away in French Polynesia. Think about the scale of that for a moment. An eruption too remote for any human eye to see was still loud enough, in the language the Earth speaks, to be heard on the other side of the Pacific. That is the defining, almost unnerving characteristic of Ahi Seamount. It does not announce itself the way land volcanoes do. There is no glow visible from a distant hillside, no plume climbing into the evening sky over a city, no evacuation siren that a government can trigger with confidence because the danger is visible and measurable. Everything scientists know about Ahi's behavior has been reconstructed after the fact, pieced together from fragments of indirect evidence. A seismic station thousands of kilometers away picking up a tremor pattern. A satellite catching a smudge of discolored water on a single clear pass. A hydrophone array built for entirely different purposes, picking up the acoustic signature of rock fracturing under the sea. Ahi does not perform for its observers. It hides, and it only reveals itself in glimpses. The next major glimpse came in 2014, more than a decade after the Rangiroa detection, and this time the evidence was far richer. Because by then, the monitoring network in the region, while still thin, had improved. From late April through mid-May of that year, seismometers on the sub-aerial volcanoes of the northern Mariana Islands and a hydrophone array anchored near Wake Island, nearly 2,000 kilometers to the east, both picked up sustained signals consistent with an eruption at Ahi. This time, there was also human testimony, and it came from an unlikely source. NOAA divers who happened to be conducting coral reef research in the waters near Farallon de Pájaros. They did not see the eruption. They heard it. Underwater, sound travels faster and farther than it does in air, and the divers reported hearing explosions, a series of concussive blasts rolling through the water from somewhere in the direction of the seamount. When scientists later mapped the underwater terrain, they found the physical fingerprint the 2014 eruption had left behind, a new crater carved near the summit, and a large landslide chute that had opened up along the volcano's southeast flank, a scar left by rock and debris sliding down the mountain's side in the aftermath of the explosions. It was the clearest confirmation yet that Ahi was not simply an ancient, extinct feature on the seafloor. It was, and is, an active vent in one of the most volcanically restless arcs on the planet, and it was capable of reshaping its own summit within the span of a few weeks. For almost a decade afterward, the pattern repeated itself, quieter stretches punctuated by bursts of confirmed unrest. The volcano erupted again from October 2022 through May of 2023, and then again from December 2023 into April of 2024. Both episodes characterized by submarine plumes visible in satellite imagery and by geophysical detections on the same Wake Island hydrophone arrays that had first caught the 2014 event. And then, in August 2024, something began that is not, as of the most recent USGS reporting in the summer of 2026, definitively ended. A new episode of unrest opened up, and it has continued in fits and starts ever since, sometimes flaring with signals strong enough to warrant a possible eruption notice, sometimes falling quiet enough that weekly bulletins report nothing more than a clear satellite pass with no visible plume. In January 2026, the pattern repeated in miniature. USGS reported a possible eruption signal detected on the 17th of that month, picked up in underwater pressure sensor data from a monitoring station near Wake Island, more than 2,000 kilometers away. Satellite imagery, even the clear, high-resolution passes, showed nothing. No plume, no discoloration, nothing a human eye could confirm. Just a signal in the data, a whisper from an instrument built to listen for exactly this kind of thing, with no way to know for certain what was happening 55 meters beneath the waves at the moment it was recorded. This is the deep structural problem sitting underneath every one of these bulletins, and it is worth sitting with because it is not really a story about one volcano. It is a story about the limits of what modern science can actually see. On land, volcano monitoring has become extraordinarily sophisticated. Around Kilauea in Hawaii, for instance, scientists track eruptions almost in real time, watching tilt meters measure the ground itself, swelling and deflating as magma moves beneath the surface, tracking seismic tremor that spikes in the minutes before lava breaks through a vent, monitoring gas emissions that shift in composition as an eruption approaches. When Kilauea entered episode 44 of its ongoing Halemaumau eruption in April 2026, scientists could describe the event almost minute by minute. The sharp increase in seismic tremor, the deflationary tilt recorded at a specific station, the moment lava fountaining began, the exact hour it stopped 8.5 hours later. That is what volcano monitoring looks like when a mountain sits on land, wired with instruments, watched by an observatory built specifically to study it. Ahi has none of that. There is no observatory perched on its slopes, because it has no slopes above the waterline. There is no tilt meter measuring ground deformation, because there is no ground accessible to plant one on. There is no direct seismic station within useful range, because the nearest solid land close enough to matter is Farallon de Pájaros, an uninhabited island with no permanent scientific infrastructure at all. Everything USGS knows about Ahi in any given week comes from what scientists call distal monitoring, meaning monitoring from a distance, using instruments that were built and placed for other purposes, and simply happen to be sensitive enough to pick up a faint echo of activity from hundreds or thousands of kilometers away. A hydrophone array near Wake Island, designed to listen across vast stretches of ocean, occasionally catches the acoustic signature of an underwater eruption, the way a distant microphone might catch a muffled voice through a wall. A satellite passing overhead on its routine orbit might, if the timing and the weather align, capture a single frame showing a patch of discolored water, where sulfur-rich fluid or ash has stained the sea a different shade of blue. That is the entire monitoring apparatus for a volcano capable of explosive eruptions, sitting less than 60 meters from open air in one of the busiest oceans on Earth. And this is precisely why the language in the July 2026 USGS bulletin carries the weight it does. The report states plainly that the summit has shallowed over the course of previous eruptions, meaning each time Ahi erupts, it builds itself a little closer to the surface, layer by layer, the same way a land volcano builds a cone with each new flow. 55 meters below sea level today. Not 55 meters, it has always been. 55 meters after decades of eruptions, steadily narrowing the gap between the crater and the sky. And then the report adds the sentence that turns a routine scientific update into something closer to a quiet warning. The lack of local real-time data means we are unable to forecast or warn of impending eruptions. Read that again, slowly. This is not a hedge. This is not scientific caution dressed up as uncertainty. This is the United States Geological Survey stating, in an official government document, that if Ahi Seamount begins to erupt violently tomorrow, there is a real possibility nobody will know until it is already happening. Now place that fact inside its actual geographic context, because the ocean above Ahi is not empty. The Mariana Islands sit along one of the busiest trans-Pacific shipping corridors in the world, a stretch of water threaded by container vessels, fishing fleets, and military transit routes connecting East Asia to the deep Pacific and beyond. Fishing boats, in particular, are drawn to seamounts like Ahi for a very simple reason that has nothing to do with volcanology. Seamounts create upwelling currents that concentrate nutrients, which in turn draw fish, which in turn draw the exact kind of small commercial vessels that have the least sophisticated navigation and monitoring equipment on board. The same underwater mountain that geologists watch with seismic instruments and satellite passes is, to a fishing crew, simply good water. There is no buoy marking the summit. There is no restricted zone enforced by patrol boats. USGS itself states the danger in the plainest possible terms. Eruptive activity at Ahi Seamount may present a hazard to mariners in the water above and near the volcano. A submarine eruption at 55 meters depth is shallow enough to generate a genuine surface hazard. Explosive gas release can send superheated water, ash, and ejected rock fragments upward with enough force to break the surface entirely, something scientists call a Surtsean eruption, named after the Icelandic island of Surtsey, which was born in 1963 when an undersea volcano did exactly that, punching through the ocean surface and building a new island out of ash and steam within days. Ahi, at 55 meters, sits well within the depth range where this kind of surface-breaching event becomes physically possible during a sufficiently energetic eruption. A boat sitting directly above the vent at the wrong moment would have no warning beyond, perhaps, a sudden and violent change in the water itself. Heat, discoloration, a smell of sulfur. The same signs that fishing crew felt back in 1979, except potentially now with the added, far more dangerous possibility of ejected material breaking the surface entirely. There is also the question of what happens to the air above the water, because Ahi's aviation color code was set at yellow for a reason that has nothing to do with boats. Submarine eruptions that breach or nearly breach the surface can loft ash into the atmosphere just as effectively as a land volcano. And ash, at altitude, is one of the most quietly dangerous hazards in modern aviation, capable of scouring cockpit windows, contaminating fuel systems, and, most critically, stalling jet engines mid-flight if ingested in sufficient quantity. The Mariana region sits beneath trans-Pacific flight corridors used daily by commercial aircraft moving between Asia and the Americas. A yellow aviation color code signals that a volcano is exhibiting signs of unrest above known background levels, elevated enough that pilots and dispatchers need to be aware something could escalate, even if there is no current evidence of an ash-producing eruption in progress. It is a warning built entirely on uncertainty, a way of saying, we do not know what this mountain is about to do, and neither do you. So proceed with that gap in knowledge held consciously in mind. Layered underneath both of these hazards is a third, quieter one that surfaces in scientific literature on submarine volcanoes far more often than most people realize: the tsunami risk associated with flank collapse. When the 2014 eruption at Ahi carved a new crater and opened a landslide chute along the volcano's southeast flank, it demonstrated something scientists already suspected about seamounts built from unstable, rapidly accumulated volcanic material. These underwater mountains do not always erode gently. Sometimes a section of a volcanic edifice, weakened by repeated eruptions, saturated with hydrothermal fluid, and steepened by decades of eruptive buildup, simply gives way, sending a massive volume of rock and debris sliding down into deep water in a matter of seconds. When that happens at a shallow seamount, the displaced water has to go somewhere, and the result can be a localized tsunami, a wave generated not by a distant earthquake rupturing hundreds of kilometers of fault line, but by a landslide happening in one specific place, on one specific mountain, with no warning system built to detect it in advance. Ahi has already proven in 2014 that it is capable of generating exactly this kind of flank failure. Nobody is suggesting that a catastrophic collapse is imminent, but the geological ingredients for one, a steep, unstable, eruption-built cone sitting close to the surface in an area of ongoing volcanic construction, are quietly present, and they sit inside the same data gap that prevents scientists from forecasting the volcano's eruptions in the first place. So what then does the advisory alert level actually mean, in practical terms, for the scientists watching this volcano from thousands of kilometers away? It sits in the middle of a 4-tier system used across the United States Geological Survey's volcano observatories: normal, advisory, watch, and warning. Moving upward as evidence of unrest strengthens and the likelihood of hazardous activity increases. Normal means a volcano is behaving within its expected quiet background state. Advisory, where Ahi currently sits, means a volcano has exhibited signs of elevated unrest above known background levels, or in the case of a volcano like Ahi, with no long history of continuous monitoring, that its behavior remains uncertain enough to warrant close watching, even in the absence of confirmed ongoing eruption. Watch, 1 level up, indicates heightened or escalating unrest with an increased potential for eruption, and warning, the highest tier, signals that a hazardous eruption is either underway or expected imminently. Compare Ahi's advisory and yellow status to what was happening at Kilauea in Hawaii in March 2026, when the Hawaiian Volcano Observatory raised the alert level all the way to warning and the aviation color code to red as episode 43 of the Halemaumau eruption sent lava fountains soaring more than 350 meters into the air, forcing park closures and highway shutdowns. That is what a warning level event looks like when scientists have the instruments to see it coming and the infrastructure to respond. Ahi sits 2 full tiers below that, not because scientists are confident the danger is smaller, but because there is barely enough data flowing in each week to justify anything higher than continued watchfulness. The alert level, in Ahi's case, is less a measurement of current danger and more an admission of how little is actually known. And this is where the story stops being about one seamount in the Mariana Islands and becomes about something much larger. Ahi is not unique. It is simply the case study currently on the record, the volcano whose most recent bulletin happened to surface in the news cycle. There are, by conservative geological estimates, tens of thousands of submarine volcanoes scattered across the floor of the world's oceans, the overwhelming majority of them never surveyed in any detail, many of them not even formally named or mapped. The vast majority sit far too deep to pose any surface hazard at all, buried under kilometers of water where an eruption dissipates harmlessly into the abyss, long before it could ever threaten a ship or an aircraft. But a smaller subset, seamounts like Ahi, sit shallow enough, close enough to the surface, that an eruption becomes a genuine hazard to human activity above. And the honest, uncomfortable truth is that scientists do not have a complete list of exactly how many of these shallow, hazardous seamounts exist, let alone continuous monitoring capability for most of the ones they do know about. Ahi happens to sit near enough to existing hydrophone and seismic infrastructure, built originally for entirely different scientific and military purposes, to generate at least a fragmentary picture of its behavior. Most shallow seamounts in the world's oceans are not so fortunate. They erupt, if they erupt, in total silence, unrecorded, unremarked. Their only trace a faint smudge in a satellite image that nobody happened to be looking at when it passed overhead. History offers a handful of comparisons, and none of them are especially comforting. In 1952, a submarine volcano called Myojincho, part of the same broader Izubonin Mariana Arc system that includes Ahi, erupted violently enough to breach the surface south of Tokyo, briefly forming a small island of ash and cinder. A Japanese research vessel, the Kaiomaru No. 5, sailed in to study the eruption up close, carrying a crew of scientists and sailors who wanted to document the birth of new land in real time. The volcano erupted again while the ship was still in the area. All 31 people aboard were killed, and the vessel itself was destroyed. A stark, documented reminder that a shallow submarine eruption is not a slow, gentle geological curiosity to be observed from a safe distance. It can happen without warning, and it can happen fast enough to take a fully crewed research ship with it. Myojincho eventually eroded back beneath the waves, its brief island life ending much as it began, but the lesson it left behind has shaped how volcanologists think about shallow submarine vents ever since. Proximity to an active seamount summit is never entirely safe, no matter how routine the surrounding waters may look on any given day. Cavachi, a submarine volcano in the Solomon Islands, roughly 9,000 kilometers to the southeast of Ahi, offers a different kind of cautionary parallel, this one written not in fatalities, but in biology. Cavachi sits at a similarly shallow depth and erupts with enough regularity that researchers have nicknamed it Sharky, after expeditions using underwater cameras discovered sharks apparently living and swimming inside its crater, seemingly undisturbed by an environment of acidic, superheated water that would be lethal to almost any other complex organism. It is a volcano scientists study specifically because it defies expectation, because it keeps behaving in ways that force a rewrite of what was assumed to be survivable near an active vent. Cavachi, like Ahi, sits far from dense population centers, monitored intermittently, understood mostly through occasional expeditions rather than continuous instrumentation. The pattern repeats across the Pacific's shallow seamounts again and again. remote location, sparse monitoring, genuine capacity for surprise. Even within United States territory, the precedent for underestimating a quiet-seeming underwater or coastal volcanic system runs deep. Kikum-Jenny, a submarine volcano north of Grenada in the Caribbean, sits at a comparable depth to Ahi and has erupted more than a dozen times since it was first identified in 1939, occasionally generating localized waves large enough that authorities have, on more than one occasion, closed a security exclusion zone around it to shipping traffic entirely, a formal acknowledgement that the risk to vessels sailing directly overhead is not theoretical. No such exclusion zone exists around Ahi. There has never been a confirmed fatality directly tied to an Ahi eruption, and nothing in the current data suggests one is imminent. But the absence of a documented tragedy at Ahi so far reflects, at least in part, simple remoteness and low traffic density in that specific patch of ocean, not necessarily any lesser physical hazard than the volcanoes that have already claimed ships and enforced exclusion zones elsewhere in the world. What makes Ahi's situation especially difficult for scientists to resolve is that the fix is neither simple nor cheap. Building a permanent seafloor observatory capable of directly monitoring a volcano 55 meters underwater in a location roughly 230 kilometers from the nearest inhabited settlement would require ocean bottom seismometers, pressure sensors, and hydrothermal monitoring equipment all engineered to survive not just the corrosive chemistry of an active volcanic vent, but the sheer logistical difficulty of installation and maintenance in open ocean, far from any port. Research cruises capable of deploying and servicing that kind of equipment are expensive, infrequent, and typically prioritized for volcanoes with a documented history of harming people directly, which Ahi, so far, does not have. It sits in a strange scientific limbo, active enough to justify a standing USGS advisory, dangerous enough that the agency explicitly warns mariners to stay clear, and yet still not quite prioritized enough within a limited global monitoring budget to receive the kind of dedicated instrumentation that would finally close the data gap driving that advisory level uncertainty in the first place. Every eruption Ahi produces adds another layer to its slowly rising cone and another data point to a scientific record built almost entirely out of secondhand signals. And every quiet week that passes without incident makes it just a little easier for the wider world to look past a warning that, in plain language, has already been given. This volcano is active. This volcano is shallow, and right now, nobody can promise they will see it coming. That is the uncomfortable center of this entire story. Humanity has mapped the surface of Mars in sharper detail than it has mapped significant portions of its own ocean floor. Spacecraft have photographed the far side of the moon down to individual craters, while an active, repeatedly erupting volcano sitting 55 meters beneath one of the busiest oceans on the planet can only be tracked through secondhand signals bouncing off instruments built for other jobs entirely. Every week, a new bulletin goes out. Most weeks, it says the same quiet thing. No plumes observed in satellite imagery, no signals detected in distal geophysical data, current alert level unchanged. It reads almost like nothing at all, a formality, a box checked and filed away. But underneath that flat procedural language sits an admission that scientists themselves have written into the record, plainly and without embellishment. We are watching, and we still cannot see. The mountain keeps building itself upward, eruption by eruption, shallowing its own summit year after year, moving fractionally closer to the surface each time it stirs. Somewhere beneath the waves, 55 meters down, in water crossed daily by fishing boats and cargo vessels and commercial aircraft passing high overhead, a volcano with at least 11 confirmed eruptions in the last 10,000 years, and at least 5 in the last quarter century alone, continues its slow, unwatched, unfinished work. Nobody knows exactly what it will do next, or when. Nobody, right now, on Earth, has the instruments in place to tell them in time. The alert stays at advisory, the color code stays at yellow, and the mountain 55 meters beneath an empty stretch of the Pacific keeps rising.